The carboxylic acids. Okay. This here is a carboxylic acid. It has a carbon with a carbonyl and a hydroxide. So this here would be butanoic acid. And it should always be terminal because 3 of the carbon's 4 bonds are used up in making the functional group. The first one, attaches it to the chain, 2 more to get the carbonyl oxygen, and the 4th for the hydroxide. But it's not actually always that simple, not always that direct. But when it is that simple, that direct, then you can treat it like an aldehyde, in that you don't necessarily need the numbers, because you can treat it as terminal. So this guy right here, 5 carbons, a carboxylic acid at either end, a COOH. So that would make it pentane dioic acid. But you can make it, a little bit more complicated. So let's go ahead and throw a hydroxide and a carboxylic acid right there on the 3rd carbon. They wanted a way to make it easier to name this, and they came up with one. Now, if that were a side chain, the carboxylic acid there on the 3rd carbon, then it would just be a carboxy group. So it should be, something like 3 carboxy, 3 hydroxy, pentane dioic acid. But instead, they wanted to give it equal weight with the other carboxylic acid groups on there. So what happens is you don't actually count the carboxylic acids as part of the main chain, and you instead treat them sort of as carboxylic acid side chains, as carboxy groups. And what you end up with is 2-hydroxypropane, because you're no longer counting the carbons that are part of the carboxylic acid. That way they're equivalent to the carboxylic acid hanging off the side there. So it's propane instead of pentane now. And so it's a 2-hydroxypropane, 1,2,3-trioic acid. I'm not a huge fan of that, but what you're going to do, that's what the International Union of Pure and Applied Chemistry has decided. Anywho, let's talk about some of the properties of these, our carboxylic acids. First off, they turn your organic compounds into weak acids, just like the amino functional group turns them into weak bases. So it's sort of the opposite of that. That proton right there, the hydrogen on the hydroxide, that is your acidic proton. And the reason it's acidic, weakly acidic, but still acidic, is that when it loses that proton, you end up with the carboxylate, or the carboxate. Carboxylate, definitely carboxylate. The anion. And there's no longer any reason to distinguish between our 2 oxygens. There's nothing bonded to either one, so you get resonance between the 2. Okay, so on the one hand, you have double bonded oxygen with no charge, a single bonded oxygen with a negative charge, and on the other hand, they've switched. So one is now the single bond with a negative charge, and the other one has the double bond. And that's why our carboxylic acids are acids. It's because of that resonance. Resonance means stability. Resonance means happy. So our carboxylic acids are stabilized in their basic form in this way, whereas acids and so on aren't. Not acids, alcohols. Alcohols aren't stabilized, except for something like a phenol, something that's attached to an aromatic ring. So our carboxylic acids are acids when a lot of other functional groups are not. Carboxylic acids also have a strong odor. It's not necessarily a nasty or unpleasant odor, but it often is. That's just because, our noses are tuned to be sensitive to things that might be good for us or bad for us, and a lot of carboxylic acids can be very, very bad for you. In some cases, for example, they are. For so smelly feet, part of that is caused by carboxylic acids being produced by the bacteria that are making the smelly feet stink. The sour sweat odor that you'll get in locker rooms, that's due to carboxylic acids that come out with your sweat. And finally, vinegar is a carboxylic acid. So it has a very strong odor. I recommend against holding vinegar right up to your nose and taking a deep whiff. It is a very pungent odor. Carboxylic acids are very, very important in nature. They're also very important in industry, but we're going to mostly be focusing on biology and biochem for this one. That 1,2,3 propane trioic acid, or 2-hydroxy 2-hydroxy propane 1,2,3 trioic acid. Well, there's a reason I'm having trouble remembering that. Well, it's because it's citric acid. That's what it's normally called. Citric acid is it's vital to our staying alive. It's also known as vitamin C. So it's pretty important biologically. Another important carboxylic acid, or I should say class of carboxylic acid, is the fatty acids. Every fat molecule is actually 3 fatty acids bound onto a glycerin backbone. And this is what a fatty acid looks like. It's a very long carbon chain, sometimes with double bonds, sometimes without, that ends in a carboxylic acid. That carboxylic acid is what makes it a fatty acid and not just a long alkene. Makes it so it can be attached to that fat molecule backbone. And now let's go ahead and segue into some of the common names. We'll be coming back to natural stuff, but first, while I have this space, here is the smallest carboxylic acid, has a single carbon atom, so it should be methanoic acid, but it's not, of course. It's formic acid. Just as the smallest aldehyde should be methanaldehyde or methanal, instead it's formaldehyde. This is formic acid. And now I can tell you why it's called formic acid and formaldehyde. It's because this is the acid that makes ant bites sting like the dickens. They hurt because, the ants inject you with acid, and it hurts. And in French, the word for ant is fourmi. So that's one way, maybe, to remember formaldehyde and formic acid. It's because they are the smallest of these things, and ants are small. Next up, we have this guy. It's the next smallest carboxylic acid. It has 2 carbons, so you should recognize that. It's not ethanoic acid. It is acetic acid. There's the acetic acid. That's what we call it in our chemistry labs instead of ethanoic acid. It's very, very common, acetic acid. But in kitchens, it's what's known as vinegar. Moving on, back to biology. Carboxylic acids are the other half of what make amino acids. On the one hand, they have an amino group, and on the other hand, they have an acetic acid group. A carboxylic acid group. The reason I was thinking acetic acid is because there's only 2 carbons. One carbon is the carboxylic acid carbon. The other one is attached directly to the amino group. It's also attached to that R side chain. That R group is what makes the different amino acids different. It gives them their differing functionalities. So that when you combine a whole lot of amino acids into a long chain, the presence of different R groups at different points along the chain are what make the different proteins different from one another. The one thing that I can tell you directly from memory about proteins is that the active sites of enzymes are going to have a lot of side chains, those R groups. A lot of them are going to be amino groups, and a lot of them are going to be carboxylic acid groups. Somehow, some way, that I personally don't know, the presence of all those acidic and basic side chains is what gives your enzyme its functionality. Let's go back to naming just a little bit. The main thing, when it's present, it's either a hexanoic acid, a hexane dioic acid in this case. That's when it has priority. When it doesn't have priority, it's a carboxy. But it's kind of difficult for those carboxy groups to show up in the things we're naming because carboxylic acids have very high priority. There's not much that I'm willing to show you that can steal priority. But what you can do is if you stick another carboxylic acid on as a side chain, if it's separated from the main chain, you can't get a trioic acid. Instead, it'll be a carboxy group on the side chain. And the thing that makes this kind of annoying is you look here, that's a 3-carboxymethyl hexane dioic acid. This, despite the fact that that side chain has 2 carbons in it. Carboxy groups, their carbon is no longer counted as part of the chain. Remember, 2-hydroxypropane 1,2,3-trioic acid. Okay, the carboxy groups made the chain shorter. The same thing happens here. So what would have been an ethyl side chain becomes a methyl side chain because of the presence of that carboxy group attached to it. Another note real quick is the conjugate base thing. These are carboxylic acids, and weak acids have a basic form. When you remove the acidic proton, you end up with the conjugate base. And if you have, say, acetic acid, then you just remove the ic acid part, and it becomes acetate. Okay, so acetic acid becomes acetate, butanoic acid becomes butanoate. It's an O8. So ethanoic acid would be ethanoate. I got confused because acetic acid is a common name instead of a good name. So propanoic acid, propanoate, butanoic acid, butanoate, pentanoic acid, pentanoate, and so on. That's important just because it'll show up again in esters as well as with these carboxylic acids. And that is our carboxylic acids. When we come back, hopefully we can take a little bit less time to consider our esters and our amides, following which we will be done with organic chemistry.